Welcome. Thank you all for joining this webinar. It's about high-speed PCB design. My name is Sadim Tiaz. I work for Elector, and I will be assisting our guest presenter, Carl Johnson. Carl Johnson works for Microchip and has been designing, testing, and reviewing PCB platforms for almost 35 years. Carl Johnson is also the one who put this presentation together, and he knows pretty much everything about our subject. Hello, Carl. How are things in Texas today?
Things are pretty nice in Texas today. It's not even 90 yet. It's not even 35 yet as far as Celsius. So it's kind of pleasant for a change. Our summer is starting to wind down. How are you?
All good. Pretty much the temperature is the same. I have the air conditioner running at 25, so it's nice. All right, so let's give a little bit of an overview of the webinar. This webinar is intended for people interested in PCB design for today's high-speed protocols. We will discuss techniques, mitigate signal degradation, industry best practices, and many other subjects that make designing a good PCB a challenge. This webinar is an introduction to Microchip University and its course on this subject. This webinar is also divided in several blocks. So to give you an idea, we will be going through a presentation prepared by Carl Johnson. And after that, we will be having a Q&A session. For those who want to join, want to go through the course, I think it's about 2 hours. And please do check it out. After the class, you will be awarded a certificate. At the end of this webinar, you can, of course, as I mentioned before, you can ask questions by typing them in the Q&A box. This webinar is also recorded and will be available on YouTube on Elector TV channel for replay. Having that said, let's start the presentation. So I'm going to should we start, Carl?
Yeah, one thing to note maybe is that this is a trimmed down version of the presentation on the Microchip U site. So if you go there, you'll get a lot more information that'll fill in extra details. So just be aware that this is a touch on the 71-minute presentation that's on Microchip U.
Yep, that's true. All right, let's begin.
Hi, my name is Carl Johnson. Welcome to my presentation, Designing PCBs for Systems with High-Speed Protocols. The course objectives for this 7-part series is that we will explore what high speed means and how it applies to PCB design. We'll identify issues when using today's high-speed protocols. We're going to outline and discuss PCB mechanisms that degrade high-speed signaling. We're going to explore methods to deal with implementing high-speed protocols. We'll share some best practices that can save you time, frustration, and money. And we'll share some documented solutions for protocol-specific issues and for general issues for further research, and so that you have some further support on what we're talking about here. We're going to use this introductory section to ground our conversation with some common language and concepts about PCB designs that use high-speed signal protocols. So, what is high speed? What is a signal? What is signal integrity? Why are transmission lines important? Now, some of this is going to be very basic. Almost all of it's going to be review for everyone here. But I think it's important for us to have a solid understanding and a language, a common language that we can use and know what we're talking about as we move forward in the presentation. So let's talk about your daddy's high speed and how today isn't that day. What is fast? In 1875, this was fast. In the signaling world, what does high speed mean? In 1844, this was high speed, 20 bits per second with a well-trained operator. That's pretty darn quick. In 2017, we went to DisplayPort, USB 3, Gen 2. DDR4 How about PCI Express? 2022, we're looking at 40 gigahertz plus DisplayPort, USB 4, DDR6, graphics DDR6, and more. Soon, what does high speed mean? Well, we know 112 Ethernet is on the horizon, 112 gigahertz. PCI 6, 8 gigabits plus. Who knows what else? The point is, high speed is relative. It changes, and we have to change our understanding along with it and our execution along with it. Yesterday's high speed issues were around the idea that high speed signals at that time operated with peak-to-peak voltages of between 3 volts and 5 volts. We had to deal with reflections, EMI, synchronizing our signals as clock matching, that kind of thing, and crosstalk. Well, today, most of those signals operate at less than 1.8 volts, often less than 0.2 volts, 0.2 volts, which means they're a lot more sensitive to corruption. We have to deal with reflections. We have to deal with EMI, same as before, and a little bit differently. We still have to synchronize our signals. We still have crosstalk. Now we have to deal with signal losses and, of course, external compliance stuff, passing eye diagrams, passing jitter specs, etc. Examples here. So the ones on the left are differential signals where we have a positive going line and a negative going line that are coupled. And USB 3, DisplayPort, PCIe, others, they use that kind of signaling. There's still a lot of single-ended signal protocols like USB HSSE, SSIC, system clocks are often single-ended that we still have to deal with as well. Differential signals make things easier in many ways, but a little bit harder in some ways. Let's talk a little bit now about PCB transmission line basics. Again, we're trying to develop a common vocabulary here. For DC signals, these are any signal that turns on, turns off, stays off, right? If we sample a line that goes high and then just sits there, and we sample a little bit later, we treat that as a DC line. So a DC line is a steady state line, and its critical characteristic that we control is resistance. An AC line, on the other hand, changes state, and it's that change that we're interested in. Going from a 0 to a 1 to a 0 is the most common example. And the critical PCB characteristic here is impedance, which is measured in ohms, much like resistance is measured in ohms. However, the resistance element of impedance is actually quite low. Capacitive reactance and inductive reactance are the big drivers to impedance. And impedance is measured on a momentary basis, moment by moment, as the signal traverses the transmission line. And keep in mind, there is always a return signal. If you don't provide a return signal path, it will find its own. Physics requires it. There is always a return signal. So, best idea for us is to plan for it. Make sure that we provide it and control it. That's one of the biggest things that I can relay about improving your designs. Make sure that your high-speed protocol designs return paths, not ground, return paths are controlled. What is a transmission line? It's any structure that guides a signal. In our case, we're talking about electronic signals. So we're talking about things like wires on telephone poles, power lines, signals that go through connectors, RF waveguides, and mostly in this discussion, we're going to be focusing on PCB traces. And we have differential pairs, which are two lines that are routed so that they do couple and are exposed to the same environments as the signal traverses from one end to the other. Or single-ended lines, which are single line that goes somewhere and its return path is defined elsewise. It doesn't have a companion signal. Now, some elements we have to deal with, high-speed issues, are out of our control. These include things like preemphasis and de-emphasis on the transmitter and receivers, whether or not a clock is embedded. The thing that we can control is the PCB structures and the transmission line structures. Once it gets out of the device and out of the software control, that's the part we're talking about that we can have some direct control over during the PCB design phase. Now, we're going to talk an awful lot about transmission lines and why. Why do they center? Why do all these discussions center on that? It's because it's the primary high-speed element that we have any control over during PCB design. Almost everything else is locked up. It's either in the design of the transmitter, design of the receiver, software control, or the chip packaging itself. We don't have any control over any of those issues. But once it makes it onto the board, now we can start exercising a little bit of intelligence on how we're going to execute those high-speed protocols. Now, for DC power, resistance is our critical characteristic, and it is driven, as you can see, by the end of this pink trace that's running across there. It's got a pink end and an orange line. That's the copper trace. The blue here in this illustration is a dielectric, and that other copper-looking area is the plane that I made reference. It's quite typical for us to have at least a plane adjacent to every signal layer. That's very intelligent design. As the trace geometry changes, it's going to affect the resistance. So the trace width and the trace thickness and the trace length all affect the resistance. As the trace width goes up, the resistance goes down. As the trace thickness goes up, the copper thickness, the resistance goes down. And lastly, as the length goes down, the resistance goes down. So the shorter it is, the less resistance it has, of course. For AC lines, it's a little bit different. The critical characteristic is impedance. Impedance is mostly driven, as I said before, by inductive reactance and capacitive reactance. So, what does that mean as far as we're concerned here in the physical world? As the trace width goes up or down, that affects it. And as the dielectric height goes up or down, that affects it. The length does not. The type of dielectric also affects it. Let's look at that a little bit closer. So as the width goes up, the impedance goes down. As the dielectric height goes down, the impedance goes down. And as the dielectric constant goes up, the impedance goes down. Air has a dielectric constant of approximately 1. Vacuum has a dielectric constant of 1. When we're looking at differential signals, there's one additional piece. It still has the same controls as impedance, plus, since it's a 2-wire interface, the spacing between those two coupled lines also has an effect on the differential impedance. So there's a single impedance for each line independently, and then there's a differential impedance for the pair. So we have exactly the same controls for the impedance and the spacing between it. As the spacing gets narrower, the fields interact more, and the differential impedance goes down. Now here we have an example of some typical transmission line structures. The one on the left is a microstrip structure. It has an outside signal, a dielectric, and a reference plane. The three on the right are all strip lines. They have signals embedded between two planes. Because the signal line in a microstrip structure only has its field going through the dielectric on one side, that actually affects the speed at which the signal can propagate down the line. In the strip line section, you have dielectrics surrounding it of a higher dielectric constant than 1. Therefore, it's going to change how fast the signal can propagate down that line. So notice that all 4 of these structures are 50 ohm single-ended impedance structures. They're actually modeled after real lines. The illustration on the far right shows an unbalanced structure where you have 2 signal lines. Each of those 2 signals is going to couple more to its nearest neighbor plane and less to the far plane, but it couples to both of them. Notice also that if you're not careful, they will couple to one another, increasing crosstalk. We'll get to that again a little bit later. And for the other 2, you can see that if you decrease the dielectric and decrease the signal width, you can maintain the same impedance. That might be helpful as you go through your design phase. Now we're going to talk about some high-speed concepts here. Signal integrity. If you can keep the signal intact so that it can be reliably received and decoded, then you maintain signal integrity. You try to reduce things like reflections, crosstalk, loss, and other effects that are going to corrupt your signal. Synchronizing signals. This is coordinating signals in the time domain, making sure that signals arrive at their destinations when they're supposed to. Clock matching is a typical example of something that we're going to use synchronizing signals on. Also, bus length matching so that an entire bus's signals all arrive at the same time. So we're trying to enable systems to actually use the signals we control at the time it expects to see them. EMI, electromagnetic interference. This could either be going out or coming back in to your system. Either way can be so bad that it'll prevent your product from shipping. So sometimes you have to be very careful. And what can we do within the limited scope of PCB design? We'll talk about that. Next is PCB structure. How PCBs are actually built, at least the part that affects high-speed signaling, and how we can use those structure details to positively affect the signals we intend to get from point A to point B so that they can properly be decoded. Let's take a quick look at transmission line reflections. So again, a transmission line is any structure that carries a signal. And it could be PCB traces, power lines, telephone wires, an RF waveguide, etc. We talked about this last time. Reflections affect the signal itself. Signal energy that we transmit down a line, effectively, bounces off incompletely terminated transmission lines. So if all the energy is not absorbed by the time the energy gets to the end of the line, it's got to go somewhere, so it comes back. And that can corrupt the shape of the signal or the amplitude of the signal that you're trying to transmit and receive. Some of that signal energy, in other words, is not absorbed by the receiver, and it reflects, hence the word reflections, toward the driving source. Here is a typical transmission line in a system. We've got a chip, and it's going to transmit a signal through a PCB trace, a connector, through a cable, into another connector, down another PCB trace to the secondary chip. So it goes from the transmitter all the way to the receiver. So as it starts out, that signal looks a little funky if you put a scope on it. Then as it moves through the system, you'll see that it actually looks like it's straightening up. As it gets to the center of this transmission line, made of several elements, we can see that it looks more and more like a regular signal, but it still has this little weird hiccup in the middle. By the time it gets to the receiver, though, it looks nice and neat and clean. The important thing is that the signal must look clean and decodable when it gets to the receiver. That's the most important element of transmitting any signal down a transmission line to any receiver. And remember, if this is a bidirectional system, as it is in this case, we need to make sure that it's clean arriving at the other end when the second chip transmits back. So we want a clean signal at the receiver at both ends. Let's talk a little bit about crosstalk. Let me introduce you to two fellows here. We have Argyle. He's a little bit loud, bossy, arrogant thing. And then we have Vinny. Vinny is just sitting there trying to mind his own business, right? But he can't ignore Argyle. Argyle's loud. Argyle's making a signal wave. And as he does this, our victim line picks up some of that field, turns it into a current, and now we have corrupted our signal. So Argyle is our aggressor, and Vinny is our victim. And remember, crosstalk can be a little sneaky. As we look at this one, we think, oh, hey, we've got a switcher circuit generating power, and here we have our powered circuit, no big deal. So there's no way we're going to have any problems, right? Our circuit in the middle, the power goes around it. Any switching noise is going to go around it, right? Wrong, because there's a return path on the plane. And remember, it's going to try to find a nice direct way to get from the powered circuit back to the switcher circuit. We have to plan on these return paths. If we don't plan for it, it's going to find its own way. And in this particular case, that noise is going to come right up from the return plane and couple into our sensitive circuit because we didn't provide a return path that was going to avoid our sensitive circuit. Here, we have that situation I discussed earlier where we have two signal lines running between two planes. This is an unbalanced strip line. And unfortunately, we ran both of these lines parallel to one another so that as the signal is generated, the field is generated around Argyle, that aggressive signal is then coupled significantly into Vinny and causes another crosstalk issue. Now, if we route these orthogonally, then it is much less likely that we'll have any kind of significant crosstalk because the time domain of an orthogonal intersection is very, very tiny. Again, it depends. It's relative. High speed is relative, and the length of that coupling is relative. The practical approach. So this approach refines the sum total of what has come before us to best practices that we can then effectively use. Simulations, calculations, observations, and measurements of people who have gone before us have given us the knowledge that we have today. Without the fundaments of math and physics, we could not have the understanding and the ease of addressing signal integrity issues that we now have today. Now, I don't want us to all be diving into the details of calculus and applied math and all the rest of that. What we want to do is take advantage of all that effort that has been done by somebody else, reduce the science and concepts that apply to high-speed signal integrity, and develop best practices. Those best practices will be critical to saving us time and money. And we want to confine ourselves to using the most effective actions. That comes into play a little later. Let's talk quickly about PCB construction. So here we see an illustration showing a simple two-layer board. It's got a silkscreen layer, a top mask layer. There's a copper sheet, core dielectric, which is just FR4, flame resistant, fiberglass and resin. Another copper layer on the bottom, solder mask and silkscreen on the bottom. A more complex four-layer board might look like this, with the center core pre-laminated and completely cured, and then semi-cured layers of dielectric added to that, and then copper foil and the other layers. All of it gets squeezed together or applied later and turned into one solid board. On the left, you see a pictorial of the copper layers and the dielectrics. Those are the parts that we're usually the most interested in when we're doing PCB stack-ups and examining board constructions for signal integrity. On the right-hand side there is a shorthand version. The narrower lines indicate signal layers, the wider lines indicate plane layers, and the spacings on the left happen to be in mils, could be millimeters, whatever. On the right-hand side, the thickness of those copper layers is given in ounces per square foot. When we talk about PCBs and executing a PCB for a system that includes high-speed designs, let's keep in mind that exotic implementations do work. What are some non-standard, unusual, or exotic implementations that address high-speed issues? Let's think about that a second. Take a moment. What are some things that are a little bit different? Things that your boss probably would not prefer you to do because of expense or other things. How about using low-loss dielectric materials like Rogers or polyimide or ceramic? How about doing 100% prefabrication PCB simulation? How about adding PCB layers? What about embedding components, embedding resistors and capacitors? And there are many other non-standard exotic implementations, and they do work at a cost, time and money. The time is also affected by how many extra details have to be done to confirm that these layers are done correctly, that the processes match the materials correctly, etc. Now, we can observe the effects of our attempts to mitigate any issues and to address high-speed signal integrity. So let's talk about an eye diagram as an example. It's a great tool. It's a type of scope trace. You generate a test pattern, and then the scope slices that up in bit times, overlays the pieces, and turns it into something you can use. So here's the USB test packet. Then those bit intervals are then cut up and then overlaid by the scope into an eye diagram, as you can see on the bottom. By examining this eye diagram, overlaying it with a compliance mask, shown here in red, we can tell whether we have any issues with attenuation, mean bit time, zero crossing, jitter, rise or fall time, and basically we just get a compliance go or no go. So we look at these two eye diagrams, we can see that the top one has an attenuation problem. The amplitude is not high enough. The mask is getting collided with at the top and bottom of that diamond-shaped piece in the middle. In this case, the cable happened to be too long, and we're getting too much loss through the cable. The bottom one shows a crossover point, and it shows that there's quite a bit of jitter. You can see how that violet moves a long way from the center here. It should be tight and clean. The tighter and cleaner it is, the less jitter there is, by definition. So we can see in this USB 2 diagram, the blue trace looks very, very clean. The jitter level here is great. Amplitude is also good. On this one, the jitter level is very high. It doesn't actually fail. It doesn't actually touch the mask, but I would consider trying to do something to address this jitter so that you have a more robust system. But again, that depends on the situation. If this is good enough, it's good enough. Good enough is. So there are 4 big system-wide effects: crosstalk, ground noise, power supply noise, and stubs. Now remember, no man is an island. We all exist and live and survive and thrive because we have the support of our communities around us. The same thing applies to signals. All signals exist within systems. No signal is actually alone. Here we saw our high-speed protocol circuits, but they're connected to other things through connectors and device cables and whatever else. But you know what? It's also part of a much larger system. And all of these system elements have effects on our system. If they didn't, we wouldn't need our circuit. Our high-speed protocol would be useless. Ground noise. Ground is everywhere in a PCB. It is a misnomer. It's not actually ground. It's a signal return. Ground is a safety thing. This is signal return. But it's normally called ground, so we're just going to call it ground for this discussion, knowing that that's not a precise detail. Ground is everywhere on a board. Local signals can pull on this ground effectively, causing currents in it. And that causes what we consider bounce. The farther away a device is from those sources, the less affected it is. Let's talk very quickly here on something called a moat. Just like good fences can make good neighbors, good moats can isolate return paths. If you do it wrong, however, you're going to irritate your neighbors. And the same thing here, if you do your moats wrong, you can actually make the situation much worse. So it's got to be done carefully. Now, a moat and a slot are different. A slot is a physical opening routed or punched through a PCB. A moat is a region of removed copper. So the layer's still there. It just doesn't have trace. It doesn't have copper in it. That prevents a current, a return path, from going across that particular region. A moat isolates power and return currents. That's its purpose. Return signals can only enter or exit, in this picture, through the opening indicated by the magenta arrow in the moat on the ground and the power lanes. That moat goes around a crystal circuit. Basically, there are a lot of high current lines on this board, and there are high current return paths. And we don't want those high current return paths interfering with the returns on the crystal circuit, so we put a moat around it carefully. Now you can see that we're going to keep those currents out. There's no traces that cross there, because if you had a trace to cross that moat, then that return current would have to loop around someplace and would then be uncontrolled. When you're doing moats, it's important that as you're trying to contain the return currents, in that case to keep the noises in, this is a switching circuit, that you've got to do it on all the layers. Otherwise, it's still going to just move around on the other layers. So in this case, layers 2, 3, 4, and 5 of a 6-layer board are all contained with moats that are equivalent on all the layers. Cables and connectors. Let's talk about these for a second. If your system has connectors, then it includes the stuff that you're connected to. Test equipment, peripherals, power supplies, other stuff. Understand those connectors and the cables in your system. Look at the drawings, look at the tech specs, tear them apart. I've looked at USB connectors as an example and Ethernet connectors and discovered that some of them are far, far better designed internally and keep the signal integrity much cleaner than others. And not always based on cost, but it is often based on cost. They correlate anyway. There's a correlation, not a causation. Signal path matters to connector routing. You got to reduce your vias and stubs and keep to one layer if possible. Keep your signals on one layer so that they don't have to change and reference different planes or different other signals. Let's take a quick look at a USB 3 connector. So in this illustration, we have a hub device on the top left, and it's soldered surface mount wise to the board, and we can see the trace is headed over, goes to the through-hole USB connector, and out. Okay, that's just great, except the through-hole pin itself on the USB connector represents a stub. There are ways that we can deal with this. Let's look at this first one. How about we put that through-hole connector on the bottom? Hey, if our system can tolerate that, if that through-hole connector can be on that side, opposite the surface mount device, now we don't have a stub. This is really quite nice. But let's say, no, you got to put it on the top. That's what the box is designed for. Okay, great. Now we're going to add, instead, an extra via. It's a longer path, but it is stubless, because now our path runs from the USB device over to the via, down to the opposite side of the board, and then catches the end of the through-hole connector and up and through. And this can often be far better than having a stub. Or how about we just go with 2 surface mount connectors? Those are all effective techniques for dealing with a stub in a through-hole device-to-connector interface. Now let's talk a real quick minute about PCB Fabricator Tour Checklist. When you go to see your PCB fabricator, number 1, do that. Number 2, make sure that you see a few items specifically. You want to investigate, get your hands on the materials that they use when they build a board. Touch the prepreg, they'll let you handle a scrap piece. Touch the parts. You can see how delicate and simple these are and how thick sometimes they are and how strong they can be. Get yourself some ideas about real world. You can see how they put these material layers into a book to laminate them to make the boards. They put stacks of these books into a large heated press, pressurize it, hold it together at fixed temperature for fixed time until the resins cure. And now it's a solid chunk of board that they can continue to process. Very often, they'll have to etch internal lines, then laminate these things together, drill the holes for the vias, plate everything together, so now you establish connectivity between layers and move forward. So you're going to see how those patterns are etched. You're going to see how panels are drilled, including multiple drill passes, laser drilling, back drilling. Ask the questions, and then take a quick look at their QA processes, including the QC processes. And you can take a look at how they do cross-sections and examine those with micrographs and other details. This stuff will give you a really good idea of reality when you're talking to your fabricator on the phone about your stack-ups and other details, trace widths, spaces, gaps, etc. Bypass. So why do we add bypass? Well, we're trying to reject noise. That's what bypass capacitors are for. They take that excess energy and shunt it so that we don't have to deal with it. Or it takes a reservoir of power energy to feed temporarily at very high frequencies into our device. We can use it for power supply noise rejection, regional noise rejection, device level noise isolation, and local or adjacent noise isolation. High-speed signals generally need high-speed noise. The higher frequency your fundamental frequencies or the higher your edge rates, the more noise you're going to have and the higher speed that noise is going to have. So one of the fundamentals of this discussion is you want your capacitors to act like capacitors. And remember, at high speeds, capacitors act like inductors. Let's take a quick look at capacitor impedance. Capacitor packages always have a parasitic inductance and resistance, which we usually ignore because we're presuming that a capacitor is a capacitor. So when we see a cap sitting on the left there, what it really is a capacitance and an equivalent series inductance and an equivalent series resistance. And all of those feed into its impedance. Now remember that inductors are wire lengths. A stretch of wire, a length of wire, whether it's wrapped in a circle or whatever, is an inductor, and they have parasitics too. Traces and vias are wire links and therefore are inductors. Now, when we put a capacitor on a pin in the schematic, we think we're doing this. Put a nice neat capacitor between V in and ground. But what we're really doing is this. And the inductors in this illustration can be very bad. All of these little magenta circled areas are traces and vias. And of all of these, only one of those can be completely eliminated. All the rest can be reduced, but only one of those can be completely eliminated. So what we want to try to do is try to make our capacitors act like capacitors. By reducing these stray inductances, the resistance makes less importance to the total interference with the capacitor function. So let's look at this illustration of a device on a board and its bypass capacitor that's routed to its power pin. So the second from the left pin is the power pin. Now we have several different sources of inductance. We've got a couple of vias, we've got the package, an ESL for the entire package, we have traces. Now what we're trying to do is keeping all of that stuff as low as possible. And this is a very well done bypass cap. The power comes from the power plane through the via right over by the ESL label, goes through the pad of the cap, and then straight on to the pin of the device. That's good. It's got two vias on the ground. Remember, those are return, but we're going to call it ground, which divides that inductance by half. So it improves that, and it also increases the capacitance of those vias by 2. So that's great. There's only one thing that I would do a little bit differently in this illustration to make it a little more perfect. That right-hand ground via would be put to the left so that the ground loop area between the power and the ground via would be shorter. The dielectric that is used to manufacture a capacitor has a different effect, especially on its value. NPO, otherwise known as COG, devices are the best, but their values are limited. It's hard to get a high-value NPO cap because you'd have to make the part actually physically larger. Now, when you use X5R or X7R materials, then that capacitance can go up quite a bit, but it's less perfect, and it varies over temperature. The NPO COG means the capacitance doesn't vary over recognized temperature range. X5R, X7R are tightly controlled, but not great. Wi-Fi V, as an example, is bad. Other dielectrics can be okay, but you got to confirm before you use them whether they're actually being effective. Aluminum electrolytic capacitors are usually bad for high-speed bypass. They have high ESR, they have high ESL, and their values and ratings are unstable over time and temperature. Now remember, the capacitor packages with wire leads have higher ESLs, and you should avoid those for high-speed bypass.
All right, so this is the end of the presentation. Thank you, Carl. It was very interesting, especially that eye charts. That was amazing. I never seen that before, so that was truly an insight for me. And now we will try to answer all of your questions. So please submit your questions in the Q&A chat box.
So let's be a little more realistic. Let's answer as many questions as we can.
Yes, of course.
This topic I have found is extremely wide and is difficult. That's why the presentation is over an hour long in the Microchip U class. It also refers to our application note AN 26.2, which I strongly suggest anybody on this call should download and review. It talks about a lot of extra details as well. But this is a beginning thing. To really get into this would take a person years if they want to understand it well, and maybe decades to really know what's going on. I don't claim to know everything about what's going on here, but I do have a lot of experience and a lot of information to share.
Yeah, absolutely. We have a question from Tony. Is there a website for more information on the eye diagram using a scope?
That's an interesting question. I would expect that the scope manufacturers who have that kind of processing power, like LaCroix and TI and other ones, will have that information on their sites. But I have never seen it. That's why I developed that slide.
Yep. Right. So we have another question from Tony. Do you need a moat around a ground plane under a high-speed signal?
Normally, no. If you control your layout with placement, and this is in one of those skipped elements of the presentation on Microchip U, there's a whole little section that talks about how to manage the layout so that you isolate circuits with placement, physically isolate them so that you don't have to have crossings. Then usually you do not want to put moats on any board. It's best if you can isolate your return currents with placement and with careful routing so that the return current is usually going to try to follow the primary path of the source current. Not always, because sometimes it'll seek a shorter path. But because it's going to do that, it's not going to go to a far corner and then come back to the supply as an example. Basically, it's going to follow the path of least resistance, specifically, to the source of the signal or the source of the supply. So you isolate those circuits with placement and with careful routing and getting your transmission lines isolated from other transmission line or high-speed noise sources that could corrupt your lines rather than put moats in. So moat should not be your number one um, attempt to try to control return currents. Number one is placement. Number two is routing. Number three is moats because, as I mentioned in the presentation, if you do it incorrectly, it will cause trouble. Right? I was working on a PC motherboard design a long time ago as an example, and we needed to keep audio noise out of the integrated audio controller that was on the PCB motherboard with all the digital stuff. And in that particular case, carefully putting a moat in solved the issue, right? And in that particular case, AMD was very happy because we were able to design a board for them that worked better than their own board. That was our goal then, was to always improve, always deliver something that was better than Intel or AMD or Packard Bell or whomever it was our customer base could do for themselves. But if you put those moats in too aggressively, it can cause return current issues with the signals that you intend to keep clean. And then you have real issues. Or worse yet, it could actually do power starving, which is power starvation is when the return path is so incongruous to the signal that you actually develop losses on the return side, and that will give you all kinds of different problems. So moating is important. Moating is extremely useful and should not be your first go-to answer. I hope that answers the question.
Yep. Okay, we have another question from Sasa. Can we use double trays, signal and return routing instead of planes?
Yes. Short answer is yes. I have successfully personally done a USB 3 Gen 2 design that had no planes at all, just two outside layers. This is not an easy task because every return path has to be very carefully considered. And when you're dealing with trying to supply 2.5 amps to each downstream port on a USB 3 hub, at the same time maintaining return current, very high return currents for those, and you're trying to keep your USB 3 Gen 2 5 gigahertz lines clean and neat and uncorrupted, it's an issue. Yes, it can be done. You just have to make sure that your return currents are planned. Like I say though, it can be done, but it is far easier to control the impedance targets, especially the differential impedance targets of differential lines, if you're using a plane. Now, the plane doesn't have to be on the inside of the board. The plane can be on the outside layers of the board and the signals can be embedded. This is a very common technique in the automotive industry because they have to control EMI so tightly. It can be difficult to do that, and it may add a couple extra layers in order to get your total signal count or your total power distribution on your system accommodated. But it can be an extremely effective way to control EMI. But again, it's going to be planes are really much easier to deal with. It makes it far easier to define the impedance of the lines, which is usually a very important element of any of these high-speed protocols. You usually have, as an example, PCIe is going to be an 85 ohm target. USB is an 85 ohm target. It used to be 90, but they've modified that. Ethernet and several other things are going to be 100 ohm differential targets. And one of the other things you need to watch out for there is what is the single-ended impedance on differential lines, because sometimes that makes a difference. Most of the time, a differential line is a line that's driven high and another one that's driven low at the same time, and they parallel one another. However, each of those is a single-ended driver, so you need to be aware of the single-ended impedance target as well as the differential impedance target. Far easier to control with planes than trying to avoid it, but it can be done.
All right. Another question. Differential signals should be on the same length? Should have the same length?
Yes. And if you take a look at, again, application note AN26.2, I actually include a chart in there that shows what we at Microchip use for our length matching. Because remember, you want to match the lengths of lines in order to match the flight time of the signals. You want the signals to go down the transmission line at the same time so that the differential pieces, the P and the N, the plus and the minus signals, are equivalent as they move down the line. That keeps them in phase, and you want them to arrive at the correct time at the other end. That's also covered in the large version of this process, of this procedure presentation. There we go. That's the right word. But in AN26.2, I actually give you that chart that shows what we match our lines to. So there's two matching that has to happen, right? So one is how different the two lines are within the pair and how much they can be a little bit different. And then again, the second piece is if you have multiple differential pairs that all have to arrive at the same time, how much can they vary? So I cover some of that in the Microchip U class and in the AN26.2 application note.
Okay, a question from Fabian or Fabian. I'm sorry if I butchered your name. Can grounding the electrical power system help eliminate or worsen the negative effects?
Okay, let's try that question again. I didn't quite understand.
Can grounding the electrical power system help eliminate or worsen the negative effects?
Well, when you're grounding the overall system, that's actually talking about true ground. Remember, in our discussion here, we decided to call return ground, right? Because most people refer to it that way. In reality, we're talking about signal return on a system. Safety ground or shield ground is a completely different topic, and how that's handled and how you manage things like near field and far field transmission of EMI signals and those kind of things is a completely separate topic, and it's a very wide and deep topic. So really can't get into it right there, but short answer is grounding to a shield, external shield, does not usually make any difference to what we're talking about with signal returns and with signal integrity, except if you do it badly, it can induce big problems into a high-speed protocol transmission line. So it must be done very, very carefully.
Yes, absolutely. We have a question from Jan. How about resonance frequencies? How to avoid standing wave occurrences?
Okay. Resonant frequencies are usually going to be restricted. Any control of that is usually going to be restricted to the die. It is not normally going to be something that we can deal with on a PCB, although there are a few things that you can do to avoid this. For instance, perfectly symmetrical return vias, ground vias, that surround a differential or single-ended line. It's really important that those not be perfectly symmetrical. As an example, I was looking at some data on a 112 megahertz test signal, and they had the launch point surrounded by 4 vias that were perfectly equidistant from that line, and it created a resonant cavity. And those energies would go out, hit the vias, and actually bounce back in, and it made a resonance cavity that gave frequencies that were not part of or harmonic to the fundamental, which it was fascinating. It's really interesting. So what's the fix though? I mean, remember, we want to take all the research and elements and the history of everyone around us and develop best practices that get away from that. We're not trying to develop the science per se. What we're trying to do is execute the science. So in this case, a slight variation of the via distances will prevent that kind of resonance cavity from forming in the first place. So you want to, and it has to be a significant difference in the distances, but not so large or so far away as to prevent the impedance control and the return control and the transmissive functions that you're trying to corral all those signals in with the via set in the first place. So yeah, it gets very, very complex. But what I do as an example, when I'm doing a transmission line that is shielded, basically it's got ground planes on both sides and it's stitched with vias, right? I make sure that I vary the position of those vias at least 5% between each via set, each via pair. And the reason for that, and they don't have to be paired. I try to offset them so they are not paired, so that these dimensions don't cause any issues as the transmission line, as the signal flows down the transmission line. However, it's always got to be, in my particular case, I like to shoot for 1/11th of the frequency. Why 1/11th? It's just a number that I know is never going to give me any resonance. So instead of using quarter wavelength, I'll use 1/11th wavelength. Personal preference. It's in my best practices and it works.
Yes, tried and tested.
Exactly.
Okay. Yeah. Okay, we have another question. Can thermal vias interfere with your digital high-speed signal?
Absolutely. But usually they don't interfere. They actually improve things, because what they do is they will tie external floods or internal planes together. And that gives you shorter return paths. Okay, so imagine that you've got a line running on layer 1, on the top layer, and you transition that to the bottom, and let's call this a 6-layer board. Well, in this case, a normal structure is going to have a plane at layer 2 and a plane at layer 5. You want to have a via right there at that same location that goes between a flood or a on the outside of the layers on 1 and 6, and tie that to the ground layer, the return path, on layer usually 2. Right? If your device is going to be on layer 1, you usually want to have your return plane on layer 2. That way you can handle some issues within the package. It's expecting a certain level of coupling to its adjacent plane, and the further that plane is away, the lower that coupling factor is going to be. So generally, it's a good idea to make your return path on 2 and the power path on 5 in this structure. The further away plane would be the power, the closer one would be the return. But in order to tie those together to give a reference path that makes sense so that your return current will flow and follow the high speed path. You want to have at least one via. And in our case, what we do is we use hyperlinks and ANSYS HFSS simulation to find out what those via and clearance structures should be so that you maintain the proper impedance and keep your insertion losses low through that via set, and have return currents that flow through those surrounding return vias. But yes, tying those together, what I like to do is I like to move them away a little bit so that I've got a nice channel that runs through there. You don't have to have them evenly spaced. I like to have them around the periphery of EPADs. And again, that's described in the larger class. And then the filling vias for thermal purposes, I like to have those set in bunches, in rows, so that there's larger spaces in between. And that works pretty darn well. On microchip devices, this is an important one. On microchip devices and on many other manufacturers' devices, the EPAD is the only return, the only ground for that part. Therefore, because what happens is we take the die and we bond it, all those VSS pins to get bonded down to the EPAD. That way we don't have to lose pin count just to have returns. So what that means is that it's really important to put your vias for the thermal vias around the perimeter of the EPAD, inside the EPAD. That's really important to keep the return loops as short as you can, and then fill it with the rest of the necessary vias to hit the thermal targets. So I know I just went down a tangent there, but hopefully that's helpful.
Yep. And that would be our final question. Other question, of course, you guys can email us and we will try to respond as soon as possible. And that's it for now.
Okay. We have, there's a lot of, did we send out a list of support documentation, that kind of thing? I don't remember. I didn't see it.
I think we should include that after the end of the webinar.
Excellent.
All right, then. Then, as I said in the beginning, that this webinar will be shared via video, so it will be available on the Elector TV channel. And also do go through the course. It's very, very detailed, and I really find it very interesting myself. All right, so I hope to see you guys again in another webinar, which in 2 weeks, if I'm not mistaken. Thank you, Carl, for doing this webinar with me. It was really interesting, and thank you everyone for attending.
And thank you guys. I appreciate the attention.